Hey everyone, welcome. So, if you've ever been in a technical interview, staring at a coding problem and just felt your mind go completely blank, yeah, you've come to the right place. Today, we're not just going to solve problems, we're going to build a playbook for how to actually think your way through them. It's all about cracking the coding interview by focusing on the process, not just memorizing the answer. So, let's dive in and build this playbook together. This is the million-dollar question, isn't it? It's so easy to fall into the trap of thinking they just want you to spit out the most perfect optimized solution right away. But honestly, that's not it at all. Interviewers are way more interested in your thinking, how you communicate, and your ability to navigate from "I have no idea" to "aha, I've got a solution." It's all about the journey, not just the destination.
Exactly. You have to think of it like a performance. You're performing your problem-solving skills live. And to really show you what I mean, we're going to run a little mock interview session right now. We'll take on 3 common types of questions, and with each one, we're going to focus on demonstrating that thought process that interviewers are desperately looking for.
Okay, first things first. Before we even look at a single line of code, we have to get into the right mindset. This is the foundation for absolutely everything that comes next. Think of this as your game plan for that performance we just talked about. It's a step-by-step guide for pretty much any question they can throw at you. First, you listen and ask questions to make sure you get it. Then, you think out loud. Your first move is to put a simple, even if it's slow, solution on the board. This just proves you understand the core problem. Then, you analyze it, talk about its weaknesses, and work with the interviewer to refine and optimize it. This is our roadmap to success. All right. Let's put that plan into action with our first question. We're going to start with a foundational, kind of warm-up style problem. These aren't designed to be super tricky, but they are a great test of your ability to handle logic and details with precision.
And here it is, the leap year check, a true classic, and for good reason. It looks simple, right? But it's got a very specific set of rules you have to translate into code perfectly. It's a pure test of your logical thinking.
And here are those rules. So, a year is a leap year if it's divisible by 4. But wait, there's a catch. It's not a leap year if it's also divisible by 100, unless, and here's the final twist, it's also divisible by 400. That's why the year 2000 was a leap year, but 1900 wasn't. This little but unless game is the whole puzzle. Your job is to turn that sentence into a clean Boolean expression.
And boom, here's how that logic turns directly into code. We're basically just writing out the rules we just said out loud. A year is a leap year if it's 1, divisible by 4 and not by 100, or 2, it's just plain divisible by 400. This kind of clean, direct translation of logic is exactly what an interviewer wants to see on a warm-up question.
Okay, warm-up is done. Now for the main event. This next problem is a genuine classic. You'll see it, or variations of it, all over the place, because it's a fantastic test of your algorithmic thinking and, crucially, your ability to go from a slow, obvious solution to a really elegant, optimized one.
The problem is called maximum subarray. You're given a list of numbers, some positive, some negative, and you need to find the connected or contiguous chunk of that array that adds up to the biggest possible number. And that word contiguous is everything here. It means they have to be neighbors, an unbroken chain. You can't just cherry-pick the positive numbers.
Let's look at an example just to make this crystal clear. In this array, you could have lots of subarrays, right? The subarray 1, -3, 4 adds up to 2. The subarray 4 is just 4. But the winner, the one with the biggest sum, is 4, -1, 2, 1, because that adds up to 6. Our job is to write a function that finds that 6.
So how do we solve this without checking every single possibility? Well, the elegant solution is a famous one called Kadane's algorithm. The logic is surprisingly simple. We're going to walk through the array keeping track of 2 things, the best sum we've ever seen and the sum of the subarray we're currently in. Now the magic trick is step 4. If our running total, our current sum, ever dips below 0, we just hit the reset button and start it back at 0. Why? Well, think about it. A subarray with a negative sum can never be the start of the best subarray. Any number that comes next would be better off starting its own new subarray from scratch instead of being dragged down. So we just drop that negative baggage and move on.
And look at this. This is the beautifully simple code that makes Kadane's algorithm work. You can see every step we just talked about. We set up our best sum and current sum at 0, and then we just loop. We add the next number to current sum, and there it is. That's the magic line.
If it goes negative, we reset it. And at every step, we check if our current sum has beaten our all-time best sum. It's so elegant, just a few lines of code.
And this is where you really shine in an interview. The brute force way, where you check every single possible subarray, that is a computational nightmare. It's O of n squared. With a big list of numbers, it would be painfully slow. But Kadani's algorithm? It's just one single pass through the data. That's O of n, or linear time. This massive leap in efficiency is exactly what interviewers want to see. It shows you're not just a coder, you're an algorithmic thinker.
All right, for our final problem, let's look at something that requires a bit of a clever trick, a non-obvious insight. This is where interviewers really test your creativity and your ability to look at a problem from a totally different angle. The question is this: how do you figure out if a linked list has a cycle in it? A cycle is just when one of the nodes points back to an earlier node, creating an infinite loop. But here's the real kicker. You have to do it without using extra memory. So you can't just keep a list of all the nodes you've seen. That's the part that makes this tricky. The solution is just brilliant. It's called Floyd's cycle finding algorithm, but most people know it as the tortoise and the hare. The idea is you create two pointers. Think of them as two runners. Both start at the beginning of the list. One runner, the slow one, moves one node at a time. The other runner, the fast one, moves two nodes at a time. And here is the aha moment. Imagine two people running on a circular track, but one is running twice as fast as the other. Will the fast runner eventually lap the slow runner? Of course, it's inevitable. The same exact logic applies here. If the linked list is just a straight line, the fast pointer will just hit the end and we're done. But if there's a loop, the fast pointer is basically running in circles, and it is absolutely guaranteed to eventually catch up to and land on the same node as the slow pointer. It's a mathematical certainty. And the code for this super clever idea is surprisingly simple. We set up our slow and fast pointers right at the starting line. Then, as long as our fast runner still has room to run, we move them forward at their different speeds. And right inside that loop, we have a simple check. Are they on the same node? The moment they are, we found our cycle and we return true. If the loop finishes because the fast runner hit the end, well, then we know there's no cycle. And this isn't just some abstract puzzle. Cycle detection is a fundamental concept in computer science. It's used for really important things, like spotting infinite loops in programs, or finding dangerous deadlock situations in big database systems where everything grinds to a halt.
So, we've tackled three pretty different kinds of problems: a logic puzzle, a classic algorithm, and a clever trick. But what's the common thread here? What are the big picture skills that apply to every interview?
Here are the most important things to remember. First, communicate. I mean it. Narrate your thoughts. Second, start simple. A working, slow solution is 1,000 times better than a broken, optimal one. Get something on the board. Then, optimize. Show them you can look at your own code and say, this is O of n squared. I know we can do better. And finally, discuss the trade-offs. Show you understand that solutions aren't just right or wrong. They have costs in time and memory. If you take away just one single thing from all this, let it be this. The code is just the final artifact. It's the tip of the iceberg. What interviewers are really trying to see is everything underneath the surface: how you analyze, how you strategize, and how you work through a problem. They aren't just hiring a pair of hands to type code. They're hiring a brain that can think. And that leaves us with one final question for you to think about. The next time you're up against a really tricky problem in an interview or just in your daily work, what's going to be the absolute first step you take to understand it before you even dream of writing a single line of code? Thanks so much for joining me.